Thank you. So first, I would like to thank the organizer for organizing this very nice event and for giving me the opportunity to talk about my research. So in this presentation, I will discuss Carrollian amplitude and their relation with the holographic correlators in ADS. So the presentation will be based on two papers, one that was done in collaboration with Lionel and Akshay, who are here, and the second one, which was done in collaboration with Fernando Alde, Marianocci, and Akshay. So let me start with some broad motivation for doing this research. So we all know this holographic principle, which states that gravity in a given space-time region can be encoded on the lower dimensional boundary of that region. And we have an explicit realization of this principle with the famous ADS-CFT correspondence. So here I will make two comments related to ADS. The first is that if you consider Lorentzian ADS, the boundary will be time-like. And the second observation is that the asymptotic symmetries in that case, namely the large gauge transformation that have an action at the boundary, are given by the conformal symmetries at the boundary. And so it means that the asymptotic symmetries in the bulk correspond to the global symmetries of the dual theory, which is a CFT. So now the question I would like to ask in this talk is how general is holography, and in particular, does it extend to the case of asymptotically flat spacetime, which are depicted here on the right. So of course, flat space is interesting because you can use them to describe a large range of phenomena that go from collider physics to astrophysics below the cosmological scale. But there are important challenges to construct a holographic model for flat space. And the first one is that the boundary, in that case, is a null boundary. So you have future null infinity with cry plus and past null infinity with cry minus. So this is very different from the ADS case. And the second important observation is that the asymptotic symmetries in that case are given by the Bondi-Metzner-Sachs group, or BMS for short. So now the question I would like to ask is how to formulate flat space holography. And by that, I mean a correspondence between gravity in asymptotically flat spacetime, and I will mainly focus on the four-dimensional case, and the lower dimensional field theory without gravity. In this talk, I will focus on a bottom-up approach, which means that I will try to deduce some aspect of a putative dual theory living at the boundary, starting from what we know in the bulk of the spacetime. And in this context, two proposals have been studied in the literature. The first one is called celestial holography. And in that case, the putative dual theory to 4D flat space is a two-dimensional CFT, which will be living on the celestial sphere. And I think Akshay will tell you more about that. But there is another proposal, which has been discussed more or less in the same years, and which is called Carrollian holography. So in that case, the dual theory is a three-dimensional Carrollian CFT that will be living at null infinity, so at scry plus and scry minus. So here are the takeaway messages from this talk. The first is that even if these two proposals for flat space holography look completely different, just even by the dimension of the putative dual theory, I will try to convince you that they are actually equivalent. So it means that you can choose either of these approaches to study the problem of flat space holography. The second important point is that I will try to describe the S matrix in the bulk in terms of correlators in the Carrollian CFT. So for the purpose of this talk, I will essentially focus on this second approach to flat space holography. And these correlators will be called Carrollian amplitudes. And then in the last part of the talk, I will explain why the Carrollian amplitudes are the natural objects which are obtained from the holographic correlators in ADS by taking the flat limit. And of course, the ultimate goal of this research is to kind of deduce flat space holography from ADS CFT by just taking a flat limit in the bulk. So let me tell you a bit more about this Carrollian physics and Carrollian holography. So here the word Carroll refers to this ultra-relativistic limit that was considered by Lévy-Leblanc in 65, and that consists in taking the speed of light, c, going to 0. So it's just a formal way to take this limit. And if you look at this limit at the level of the Poincaré algebra, you will find that the translation and rotation generators are not affected by the limit. There is no c in these generators, but the boost generator will be affected. And at the end, you will obtain what we call the Carrollian boost. So if you look at the action of the Carrollian boost on the coordinates in the space-time, they will act in the following way. So you see that they only affect the time coordinates, but they do not affect the space coordinates. So you can see these Carrollian boosts as the opposite of what we call the Galilean boosts, which are obtained instead by taking the limit c going to infinity, starting from a Lorentzian boost. Okay, so they only affect the time and not the space. Now, if you implement this limit at the level of the Poincaré algebra, you will find the following commutation relations. So this defines for you the Carrollian algebra. And this can be seen as an Inonu-Wigner contraction of the Poincaré algebra. So in particular, you can see that the Hamiltonian is the central term in this algebra, and the boosts commute with each other. So there is an analog discussion at the level of the conformal symmetries. So if you start instead with SOD, 2, which is the conformal algebra in d dimension in a Lorentzian space-time, and that you take this c going to 0 limit, you will get what we call the global conformal Carrollian algebra. And this is just obtained from this Carrollian algebra by adding the dilatation generator and the Carrollian spatial conformal transformations. So another way to see this limit is to look at the causal structure in the space-time. So if you start with a relativistic theory, where you have some light cones, and that you take this c going to 0 limit, what will happen is that the light cone will basically shrink in 2 lines. So it means that in a Carrollian space-time, particles are not allowed to move. It's kind of we say that the theory is ultra-local in that sense. So what is the relation between this Carrollian physics at null infinity? So if you implement this limit, c going to 0 at the level of a metric, and here I'm taking the simplest example of the Minkowski metric, what you get at the end is a degenerate metric, which has no leg in the time direction. So it means that this metric cannot be inverted on the space-time because it's degenerate. So if you don't want to lose any information in the limit, you also need to consider the Carrollian limit on the inverse metric. And what you get, if you do that, is a vector field which has only leg in the time direction. So it's precisely in the kernel of this degenerate metric. And this allows me to define more generally what I mean by a Carrollian geometry. This is just the data of a degenerate metric, QAB, and the vector field n, which is in the kernel of the metric. And since I told you before that null infinity, so the boundary of flat space is a null hypersurface, you can show actually that this is the kind of geometry that will arise at the boundary of flat space. And indeed, more precisely, by using the conformal compactification of asymptotically flat space-time, you can show that you have conformal Carrollian structure induced at scry. So conformal because you always have this freedom to use a different conformal factor for the space-time. So using this picture, you can see the BMS symmetries, which are the asymptotic symmetries in flat space, as the conformal symmetries for this Carrollian structure at scry. So they will preserve the degenerate metric and the vector field up to some rescaling. And so this allows me to state this important isomorphism between the BMS algebra in d+1 dimension of bulk and the conformal Carrollian algebra in d dimensions, which is defined intrinsically at the boundary of flat space. So this is the seed of this Carrollian holography proposal. So Carrollian holography suggests that gravity in 4D is dual to a field theory that is living at scry, and that involves these BMS symmetries as global space-time symmetries. And we call such a theory a Carrollian CFT. So this is just a name to denote a theory which exhibits these BMS symmetries. And we have examples of Carrollian CFT in the literature, which are usually constructed by taking the speed of light going to zero, starting from standard relativistic CFT. So we have a constructive way to build these kind of theories. And let me also say that this Carrollian holography approach follows a similar pattern than the IDS CFT correspondence, because it's a codimension 1 holography. And as I will argue in the last part of the talk, is that there is a natural relation between the flat limit in the bulk to go from ADS to flat space and the Carrollian limits at the boundary, which allows me to start from the CFT, living at the boundary of ADS, and obtain this Carrollian CFT at the boundary of flat space. But the question I would like to ask now is, can we encode the bulk S matrix into boundary Carrollian CFT correlators? So correlators living at scry and which can be interpreted as living in a Carrollian CFT. So to do that, I will work in the so-called boundary coordinates, which are well adapted to approach null infinity. And they are given by these coordinates here. So the U coordinates basically is a null time along scry. R is a coordinate that allows you to approach the boundary. So you can take R going to plus infinity to reach scry plus, but you can also take R going to minus infinity to reach scry minus. Okay? And Z bar here are just the coordinates on the celestial sphere. So the Minkowski metric in these boundary coordinates take the following form. So it's quite simple. And what you can do is to push this metric at the boundary, so taking R going to infinity, and you recover this Carrollian metric that I was mentioning before. So this Carrollian structure, which is made of this degenerate metric with a 0 in front of the du square, and N, which is a vector field in the kernel of this metric. So notice that this coordinate system covers all Minkowski space and therefore allows you to go from scry minus to scry plus by following some null direction in the space-time. So the BMS symmetries, which are the conformal symmetries for this Carrollian structure, will be parameterized by the following functions. So you have the T functions, which depend on Z and Z bar, the coordinates on the celestial sphere. And these are called the supertranslation parameters. But you also get the Y and Y bar function here, which are called the superrotation parameters. And they satisfy the conformal Killing equation in 2 dimensions. And basically, these superrotation essentially generate the conformal transformations on the celestial sphere. So now the strategy to build my Carrollian CFT operators living at the boundary is to start from the bulk operator and then take the limit R going to infinity to obtain the boundary value. And then I will identify this boundary value with what I will call the Carrollian primary. So let me start with a spin S field in the bulk. So it can be a scalar, a gluon, or a graviton. And I can expand it in plane wave, as usual, with some creation and annihilation operators. And here I will use the following parametrization for the momenta. So since it's a massless field, I can parameterize it by the energy, omega, and Q mu, which will indicate the direction on the celestial sphere for this null momentum. Epsilon here is just the polarization tensor of the field. So now if I take R going to infinity on this expression, I obtain the boundary values of the field at scry plus by taking R going to plus infinity, and at scry minus by taking R to minus infinity. And I can express these boundary values in terms of the creation and annihilation operator, which will define the initial states for the scattering, okay, between scry minus and scry plus. So now one more piece to define my holographic dictionary. So you can introduce a notion of conformal Carrollian primary field, which will be very similar to the notion of primary in a 2D CFT. So basically, you will require that the field transforms in the following way under the action of the BMS or conformal Carrollian symmetries. And they will be parameterized by So you recognize here the t, y, and y bar functions, which are these BMS parameters. And there are also some weights, k and k bars, which are called the Carrollian weights. So these are the analog of the conformal weights in 2D CFT. So let me just say that this kind of transformation can be deduced from a Carrollian highest weight representation, which looks very similar to the highest weight representation in 2D CFT, except that you get an additional condition coming from the super translations. And these representations have nice properties, and for example, they've been shown to be unitary. So now the kind of correlators that I would like to consider here are correlators at the boundary of these Carrollian primaries. Okay, so these are the kind of correlators I'm interested in. Okay, so now I have all the ingredients to state my dictionary. So first, the Carrollian operator that I've just introduced will be identified with the boundary values of the bulk field obtained by taking this larger limit. So that's my first piece of the dictionary. And this implies that the Carrollian weights that are appearing in this transformation of the Carrollian primary, the K and the K bar, will be completely fixed in terms of the helicity of the bulk field. Okay, so J here is the helicity of the field. And epsilon just tells you if the field is, if the boundary value is incoming or outgoing. So inserted at scry minus or scry plus. So if you are familiar with gravity, this Carrollian operator will just correspond to what we call the asymptotic shear. So now the second piece of this holographic dictionary is the following. So you can start with the usual scattering amplitude expressed in momentum space. So here I'm just using the parametrization that I introduced before for the momenta of the particle. So they are parameterized by omega, z, and z bar. J is the helicity, and epsilon tells you if it's incoming and outgoing. And what you can always do here is to perform a Fourier transform on this scattering amplitude to get an object here which lives in position space at scry. So it only depends on u, z, and z bar, the coordinates at non-infinity. And so here the holographic input will be to identify this object in position space in terms of a correlator of Carrollian primary in the sense I defined it before. So at this stage, it's just an identification for the holographic dictionary, and that's why I will call this object a Carrollian amplitude. Okay. So let me also mention that this dictionary between Carrollian correlators and the usual amplitude ensures that if you take a correlator in the bulk and that you push it at infinity by taking a larger limit, you recover these Carrollian correlator at scry. Okay. So let me also say that these definition of Carrollian correlators are compatible with the ward entities of a Carrollian CFT in 3 dimensions. So they basically read like this, which means that this identification actually makes sense. And a bit like in a 2D CFT, the low point correlation functions will be completely fixed by the conformal Carrollian symmetries. And the higher point function will give you some non-trivial information about the dual theory. So in particular, if you try to solve the ward identity for the 2-point function, there is already an interesting story here, is that there is 2 branches of solution. Okay, so the first branch of solution will be called the electric branch. It will be U-dependent, so it will depend on this null coordinate at scry, but it will involve this delta function with respect to the angles on the celestial sphere, so with respect to z and z bar. But there is a second branch, which is called the magnetic branch. And this time, this branch is U-independent. And it corresponds to the correlator of a 2D CFT, so a CFT living in 1 dimension lower. So I will show in the following that the branch which is relevant for the scattering is actually this electric branch. Now just a word about the celestial amplitudes. So usually the celestial amplitudes are defined by taking the Mellin transform on the usual scattering amplitude instead of the Fourier transform. And you can reinterpret this Mellin amplitude in terms of a correlator of celestial CFT primaries inserted on the celestial sphere. So these operators now depend only on Z and Z bar. So now if you want to make the relation between Carrollian amplitudes, which are living in position space at scry, and celestial amplitude, which are living in Mellin space, then basically you can take the combinations of these two integral transforms, so the Fourier transform and the Mellin transform, and this is what I'm doing here. So this allows you to map the Carrollian amplitude on the celestial amplitudes. You can also write this relation at the level of the operators, which are inserted inside of the correlators. So in the right-hand side, you have a Carrollian operator, which is rarely living at scry, so it depends on U, Z, and Z bar. And in the left-hand side, you have this CCFT operator, which depends only on Z, Z bar. And basically what this integral transform does for you is that it trades the U dependence of the Carrollian operator for the conformal dimension of the celestial CFT operator. And this is one of the reasons for which you get a continuous spectrum for the celestial CFT operators. Another important remark, if I start with a Carrollian primary, phi, and that I take some du derivative, you can show that it's still a Carrollian primary. So in a standard CFT, you would expect to get some descendants. But here what you can show is that this object still transforms as a Carrollian primary, as I defined it before, except that the Carrollian weights will be shifted. So that's one of the particularities of a Carrollian CFT. And in particular, it means that the following correlators here, where you take du derivative of the inserted operator, will also have some nice transformation properties. And this integral transform actually relates to what we call the modified Mellin transform in the literature. And it will be important for us, even if this is just redundant, because we are taking some du derivative of the Carrollian amplitude. This will be important to get rid of the IR divergences that will appear in the explicit computations. Okay, so maybe let me give you some examples of Carrollian amplitudes, and I will start with the simplest example, which is the two-point function. So you can express this two-point function in momentum space in the following way. And then you can apply the receipt, so apply two Fourier transform on this expression to get an object that is living in position space at scry. So the first Fourier transform is easy to perform because of this delta function with respect to the energy. But the second Fourier transform is a bit more complicated because of this 1 over omega pole here that is appearing, which means that this expression is actually formally divergent. So a practical way to deal with this divergence is just to use the receipt that I was providing here, namely taking some du derivative of the Carrollian amplitude. And this allows me to remove this pole in 1 over omega by just taking some derivative respect to U1 and derivative respect to U2. So M1 and M2 just count the number of derivative I'm taking on this expression. And at the end, you end up on this beautiful expression for the Carrollian two-point function. And this corresponds exactly to this expression that I obtained here from the Carrollian CFT Ward identities. So everything is consistent with the symmetry. And we know that the Carrollian CFT that is describing the scattering is an electric Carrollian CFT. So notice that you can also apply this correspondence between Carrollian and celestial holography to compute this celestial two-point function, and that you want to reinterpret as a two-point function in the 2D CFT. The problem is that you see that you get this delta function here for the two-point function, which is something a bit exotic from the point of view of a 2D CFT, and that's why I think this Carrollian picture is kind of natural to deal with this holographic dual theory. Let me give you some more complicated example. You can compute, for instance, the 4-point contact diagrams for a scalar field, a massless scalar field, and you can just apply 4 Fourier transform in the way that I described before. And the key ingredient is to use the following parameterization for the delta function. So it's the momentum conserving delta function. And when you do this explicit computation, you get this expression for the Carrollian amplitude. So you can understand this expression by splitting it in 3 parts. The first part here is just a delta function, z minus z bar, where z and z bar are the 2-dimensional cross ratio on the celestial sphere. Then you get a bunch of theta functions that are constraining the kinematics. And finally, you get this more complicated expression that depends on u, z, and z bar. So let me also say that we get similar results for the exchange diagrams. We also computed the Carrollian amplitude for the endpoint MHD amplitude. So here I'm giving the example of the gluon amplitude. So these are the usual Park-Taylor formula on which, again, you can apply these Fourier transform and use the following parameterization for the delta function to get an expression in position space. And it's kind of a very compact expression, especially if you compare it with the celestial expression that was obtained before and that involves some hypergeometric functions. Okay, questions on this first part? So if not, let me go into this second part of the talk, which concerns the flat limit of ADS correlators. So here, the holographic correlators in ADS are CFT correlators in position space computed via ADS written diagrams in the bulk. So that's the way to get these holographic correlators. And I will argue here that the Carrollian amplitudes, which are position space amplitudes, are the natural objects obtained in the flat limit of these holographic correlators. So here again, you can use these boundary coordinates in ADS. They also exist in ADS, and in that case, the metric takes the following form. So you see that the only difference compared to the Minkowski metric is this term in du square that involves this L square. So this is the ADS radius. And so you can show that the boundary coordinates in ADS cover a global patch. So when R is positive, it will cover the first Poincaré patch. And when R is negative, it will cover the second Poincaré patch. So in particular, if you want to relate these boundary coordinates with the Poincaré coordinates, you can just do the following diffeomorphism. And you can map this well-known metric on this boundary metric in ADS. Now let me make a comment. If you start with the bulk ADS metric, and that you take the flat limit, so L going to infinity, this term will just disappear, and you recover the flat space metric, as it should. But it means that the boundary coordinates have a smooth flat limit, which is not the case, for instance, if you are working with the Poincaré coordinates. So it's a useful setup to study the flat limit. And if you first consider the boundary metric in ADS, so here I'm pushing this bulk metric to infinity, and I get this Lorentzian metric at the boundary, and that you implement again the flat space limit in the bulk, then at the boundary, you see that this corresponds exactly to a Carrollian limit that I presented at the beginning of the talk. So in particular, in the limit, you get this degenerate metric with a 0 in front of the du square. So that's what you get at the boundary of flat space. So it means that you have a kind of correspondence between flat limit in the bulk, L going to infinity, and Carrollian limits at the boundary, which amounts to take the speed of light to 0. So you can show that this observation extends perfectly to asymptotically ADS solutions of Einstein's equation. So this is a very general statement at the level of Einstein's equation. And so the question I would like to ask here is, does this correspondence between flat limit in the bulk and Carrollian limit at the boundary also work at the level of the amplitudes? So the strategy here will be first to study the flat limit of the ADS written diagrams in the bulk. And then I will show that this flat limit will actually correspond to the Carrollian limit taken at the level of the CFT correlators at the boundary. So first, the flat limit. to do that, I have to consider the building blocks of the ADS return diagrams, which are the propagators in ADS. So first, the bulk-to-bulk propagator for a massive scalar field in ADS4 will solve the following massive Klein-Gordon equation with a source term here in the right-hand side. And if you express this box operator here in boundary coordinates, you will see that it takes the following form. And in particular, if you take L going to infinity, you see again that it's a nice feature of the boundary coordinates is that this box operator will admit a well-defined flat limit, and this will correspond to the box operator in flat space. Another important observation is that the M square here can be related to delta, the conformal dimension, and L square, the ADS radius. So again, if you take L to infinity, you see that you can start with a massive field in ADS and obtain a massless field in the flat limit if you don't rescale delta. So if you keep delta in as it is in the limit. So this is what you get in the limit. And the solution of this equation is just the Feynman propagator. So this is what we expect, the Feynman propagator for a massless field. And you can actually show that this limit also works at the level of the solution themselves. So you can really solve this equation for the bulk-to-bulk propagator and implement this limit, and you will exactly recover the Feynman propagator. And in particular, the information about delta will completely disappear in the limit. Okay? So it does not matter the original mass here in ADS. You will always end up on the massless Feynman propagator using this prescription for the flat space limit. So now to obtain the bulk to boundary propagator in ADS4, the usual way to do it is to take one of the points to infinity. So R1 going to infinity, for instance. And you can rescale this bulk to bulk propagator by some factors to obtain some finite results. So that's how you get the bulk to boundary propagator in ADS. You can obtain the bulk to boundary propagator in flat space in a similar way by just taking R to infinity, starting from the Feynman propagator. And now if you implement the flat limit at the level of the bulk to boundary propagator in ADS, you don't exactly find this bulk to boundary propagator in flat space. There is a subtlety here. You find this expression up to some derivative acting on the bulk to boundary propagator. Okay, so that's what we get. So in some sense, if you start with the bulk to boundary propagator, you are not completely losing the information about delta, the conformal dimension. It's just encoded in the number of derivatives you take with respect to u in the limit. Another important thing is that here I'm considering essentially some outgoing bulk to boundary propagator, but there is an analog discussion for the incoming bulk to boundary propagator, and it's again related to a sign of epsilon. And here I basically took R1 going to plus infinity, but in principle you can also take R1 going to minus infinity, or R2 more precisely, to get the incoming bulk to boundary. And this allows me to introduce this important figure, which summarizes the prescription for the flat limit that we are taking. So starting from ADS, we have only one boundary, but we have 2 Poincaré patches to cover one global patch. So basically, if you will insert some operator on the first Poincaré patch, they will be labeled by an epsilon, which will be +1. And you can show that in the flat limit, these operators will be mapped on outgoing state as cry plus in flat space. And similarly, if you insert the operator on the second Poincaré patch, that will be characterized by this epsilon equal to -1, this will be mapped on scry minus, so the incoming state for the scattering. So this is just a summary of what is happening when you take the limits at the level of the propagators. And since these are the building blocks for the ADS return diagrams, I can now study the flat space limit at the level of the ADS return diagram. So here I'm taking the example of a 4-point contact diagram, which is just an integral over ADS of a bunch of bulk to boundary propagators. And if you take the flat limit, I just told you that you obtain basically the bulk to boundary propagator in flat space up to some derivative acting on them. So this is what you get here. You get in the flat limit an integral over flat space of a bunch of bulk to boundary propagators in flat space. And you can show that this expression here corresponds exactly to the Feynman rules adapted to the Carrollian amplitudes. So these amplitude in position space that I was providing before. So it means that the flat limit in bounding gauge is working perfectly. You can go from the Feynman, from the ADS written diagrams and recover the Feynman rules in the limit. So that's a bulk argument. So now what I would like to do is to understand this limit at the level of the boundary. So the question is, can we start from a 4-point function living in the CFT, implementing the Carrollian limit in the dual theory, and obtain this Carrollian CFT correlator that corresponds to an amplitude in position space. So that's what I'm going to study now. So first, let me start with the 2-point function. And here I'm interested by 2-point function in Lorentzian signature. So there are two ways to do it. Either you start with the expression in Euclidean signature and you take the analytic continuation, or you can directly compute it in ADS, starting from the bulk to boundary propagator and taking one of the points to infinity. And so this is what I'm doing here. So you get a boundary to boundary propagator, which is just a 2-point function in the CFT. So now I will use this identification between the ADS radius. So it's a formal identification between the ADS radius in the bulk and the speed of light at the boundary, which is the parameter that is used to take this Carrollian limit. And what you can do is to implement this Carrollian limit at the level of the 2-point function. So there is a naive result that you will get in the limit by just setting this term here that involves the c square to 0, because I'm taking a c going to 0 limit. This corresponds to the magnetic branch. Okay, so this is one of the solutions of the Carrollian CFT ward identity. But if you are a bit careful, you also get this other branch, which appears when you take Z1 equal to Z2. And this actually corresponds to the electric branch of the Carrollian CFT ward identities. And this is the branch that will be relevant for the scattering. And indeed, the electric branch is the leading term in this Carrollian limit. So this is what we want to get to recover the amplitude in flat space. So if you rescale the CFT operator in an appropriate way, you can relate them with the Carrollian primary that I defined before in the talk. So you just have to take a bunch of du derivative and rescale them with a factor of c. And if you do that properly, you can actually map this 2-point function living at the boundary of Lorentzian ADS to this 2-point function living at the boundary of flat space, which is expressed in position space. So it's the 2-point Carrollian amplitude. There is a similar story for the 3-point function, and you can work in 2-2 signature to get some non-trivial results. But let me here focus on the 4-point contact diagram for the scalar field. So the 4-point contact diagram can be computed again using these Witten diagrams. And they are usually computed in Euclidean signature, and they involve a bunch of D functions. Okay, so these D functions are parameterized by delta, the conformal dimension of the external legs. And this N4 here is just a global factor. Sigma delta is just the sum over the dimension, and U and V are the cross ratio. So an example of such a D function is given here. So it's expressed in terms of log and dilog. And you can introduce these variables, Z and Z bar, which basically encode information about the cross ratio. So now the first step is to go into Lorentzian signature, because this expression is valid only in Euclidean signature. And to do that, you have to do an analytic continuation, which is a very subtle story. You have different possibilities of analytic continuation. And for instance, you can implement one of analytic continuation that will lead to the following modification of the D functions. And in particular, you see that this analytic continuation will involve some singularities in Z minus Z bar. Okay. So these singularities were not there in the Euclidean case, and they are only appearing in the Lorentzian signature. And these are called the ballpoint singularity. So this singularity will be extremely relevant for us to study the flat space limit. So in practice, you can isolate the leading singularity, which is obtained in that way. And for the example that I was showing, when you take all the delta equal to 1, you get this leading singularity here. So now an important remark is that you can express these uppercase Z and Z bar in terms of the boundary coordinates. And in particular, what you can show is that if you expand this in terms of power of C, you get a leading term, which is Z minus Z bar, which are the 2D cross ratio on the celestial sphere. And then you get a bunch of terms which are of order C squared. So it means that if you take the flat limit on the support, or the Carrollian limit on the support of Z equal to Z bar, this corresponds to isolate the ballpoint singularity, so to pick up the leading singularity in the expression of the correlators. And remember that this Z minus Z bar is exactly the delta function that is appearing in the expression of the 4-point Carrollian amplitude for the contact diagrams. So that's what we are going to do, is to study the Carrollian limit on the support of Z equal to Z bar. And once you do that, you can show that indeed the leading singularity reproduce this delta function here of the cross ratio in 2D. And there is also an explicit coefficient in front of the delta function that you can compute very explicitly. And this is exactly the coefficient that appeared in the expression of the 4-point function in flat space. Remember that the only missing piece to get the 4-point Carrollian amplitude in flat space is a bunch of theta functions, but this one can be essentially reproduced by discussing the analytic continuation to go from Euclidean to Lorentzian signature, and you can see that you only get some non-trivial Carrollian electric branch on the support of this theta function. So at the end, this is the result that you can state. You can start with this CFT 4-point function, compute the Carrollian limit explicitly, and get the Carrollian 4-point function living at the boundary of flat space. So this is a computation that is done intrinsically at the boundary, and which indeed demonstrates that the flat limit in the bulk of the correlators correspond to the Carrollian limit at the boundary. So here I was discussing contact diagrams, but you can also discuss the exchange diagrams. Basically, you can express these exchange diagrams as a sum of contact diagrams if the delta satisfy the following conditions. So here, this is the delta of the exchange operator. But I told you before that in the flat limit, the information about this exchange operator completely disappear because we go from massive fields to massless fields in the limit. And so it means that you can always choose this delta such that this is satisfied. So it means that we can also achieve explicitly this Carrollian limit at the level of exchange diagrams that works perfectly and that reproduce the desired Carrollian correlators. Okay, so let me just summarize what I said in this talk. So I've tried to convince you that there were two approaches to flat space holography, namely this Carrollian holography proposal and this celestial holography approach. And I said a word about the relation between the two. So actually they are completely equivalent, which means that we can choose either of these approaches. I've tried in this talk to convince you that the Carrollian holography approach was useful to tackle the problem of flat space holography. And in particular, we were able to encode the bulk S matrix in flat space in terms of Carrollian CFT correlators living at null infinity, so living at the boundary, in the same way that we can encode that we have holographic correlators in ADS. I've also showed that there is a natural correspondence between flat limit in the bulk and Carrollian limit at the boundary, and that this correspondence works perfectly at the level of the holographic correlators, okay, starting from ADS and taking the flat limit. So now, of course, the perspective is how far can we go? Can we take the flat limit of the ADS-CFT correspondence and find some top-down model for flat space holography? So that's actually something that we are investigating right now. Okay, so that's all I wanted to say. So thank you very much for your attention.
Great. Thank you for this very nice talk. Are there questions? Yes.
For the nice talk. I'm a bit confused about the flat limit of Witten diagram. So if I have understood well, you start from a Witten diagram, which is a correlator in D dimensions. And then, yes, and then you perform the flat limit. You don't get an amplitude in D plus 1 dimensions, but you get a Carrollian correlator which still lives in the dimension. Is it true? This is my understanding.
So this object is computed. Oh, sorry, I didn't. So this object, this ADS Witten diagram, is computed in D plus 1 dimension. So for the example I'm mentioning here, it's 4
yes,
dimensions.
but represent the correlators in D dimensions.
Right, that's right. And the left-hand side is in D dimensions. So when you take the flat limit, you get here an expression which is computed in 4 dimension or D plus 1 dimension of flat space. So that's really a flat limit. And this actually corresponds to the Feynman rules expressed for the Carrollian amplitudes. So the right-hand side here is really in D plus 1 dimension, but the left-hand side, which is the level of the correlator, are in D dimensions. Okay.
Okay, okay, thank you.
Thank you for the nice talk. So celestial chiral algebras are perhaps naturally thought of as living at the boundary of a 3D mixed topological holomorphic theory. And that 3D theory will have Carrollian symmetry. I mean, it will have a lot more, but it will certainly be Carrollian. So is there any connection between those two things?
So several times I got this question about the relation between the magnetic branch of so here I was mentioning that there were 2 branches.
Yeah, they seem like they'll be magnetic actually.
There is the electric branch, which is the one which seems to be relevant for the scattering amplitude, but there is another one, which is the magnetic branch, which does not depend at all on U. So this kind of extra dimension in the story is maybe can be maybe interpreted as a topological dimension in some sense.
Sure.
So maybe that's the connection I could see in that context.
Yeah.
But at least at the level of the scattering amplitude, this is the branch that is relevant. I expect that this magnetic branch will be more relevant to the soft sector of the scattering.
Okay, yeah, that makes sense.
That's maybe the relation.
Thanks.
Are there more questions? Yes. Okay. Yeah.
So did you see any connection with Mellin amplitudes in ADS? I mean, do they, at least maybe you mentioned them and I didn't notice, but.
Right. So there are different prescriptions to take the flat limits. Here we stay purely in position space. We don't go into Mellin space and then take some kind of flat limit. So we always stay in position space from the beginning to the end. We are never going into this Mellin space.
But you don't. But you didn't investigate connections with the Mellin amplitudes then. Or...
You mean the Mellin amplitude in flat space, or
no? I was thinking more the
no.
The ADS version.
No.
Which seems to be sort of relatively ubiquitous there, or
right?
Or more popular there.
There is also the story of the ballpoint singularity that is arising in that case. That plays an important role if you want to recover the flat limit of the correlators. But we didn't investigate this precisely.
You have discussed just the massless case.
Yes.
Okay. In the case of massive case, where lives the dual theory? Because I have seen that in some paper they say that lives in E plus, E minus. In other paper they say that lives in E0. So I am confused.
Right. So I should confess that for the massive case, I don't have much to say because I think for the Carrollian amplitude, it's a bit more complicated. One thing that you can do is to define the external state at I plus and I minus. And you can show that you also have some kind of Carrollian geometry there, which is a bit more complicated because it's not a geometry living in 3 dimensions, but it's also living in 4 dimensions. So you have this tied geometry. So I think that the story is not complete at this stage for the massive particle, but it's a very interesting question. How to generalize the story for the massive amplitudes. Yes.
Comments, questions, more? Quick. Okay, I don't see any more questions, so let's thank the speaker again.